Hello and welcome to Oceanic Echoes podcast. I'm Grace. Today I'm going to share about internal waves. In oceans and lakes, water is separated from air by a free surface, and the undulations of this free surface are most commonly known as waves, i.e., the surface waves. However, this is not the only type of water waves. Within the water column, differences in temperature and salinity can give rise to situations in which lighter water lies above heavier. At such interfaces, waves can also occur, and these are called internal waves. As density differences between such internal layers are much smaller than between air and water, the gravitational restoring force, the force that acts to bring a body to its equilibrium position, is much weaker. These internal waves can easily have dimensions greatly exceeding those of surface waves, while the time evolution and propagation is much slower. According to their amplitudes, they can be divided into two types, linear and nonlinear. Linear internal waves are waves with very small wave amplitudes and can be described by linear theory. Nonlinear internal waves, on the other hand, are waves with large enough amplitudes that nonlinear effects have become important. As their name has suggested, they can only be described by nonlinear theory, and their propagation speeds are always larger than what linear theory predicts. One type of nonlinear internal waves is called internal solitary waves, waves that are well separated and in which the non-hydrostatic dispersion balances with nonlinearity. Non-hydrostatic dispersion is the effect that tends to spread out the internal wave, whereas the nonlinearity tends to steepen the wave. Therefore, the two effects are balanced, and the wave form is preserved while traveling over a long distance. Although the internal wave is below the water surface, very often it can be seen from above with naked eyes. When there is an internal wave inside the ocean, it induces currents inside, and thus convergence and divergence are formed. For example, if the water travels towards you, you will see the convergence zone first, in which the internal wave has caused a downwelling of water and so a rough water surface. Then you will see the upwelling of water in the divergence zone that comes after the convergence, so the water surface will smooth in this area. The wavefront is dark and the back is bright to human eyes, while to star satellites, which are commonly used among physical oceanographers who study internal waves, the bright and dark bands are opposite to human eyes, i.e., the wavefront is bright and the back is dark. Internal waves are a widespread geophysical phenomenon. They exist in coastal seas, straits, continental shelves, lakes, and atmospheric boundary layer, etc. Their existence does not necessarily require strong stratification, as long as there is stratification and disturbance. They can be found in any kind of continuous density stratification, especially near abrupt topographic features such as straight sails, continental slopes, or sandbanks. So the question is, why do we care? Or what's special about internal waves that keeps on attracting oceanographers? One of the many examples of their biological impact is the evidence that large internal waves can transport nutrients for sea creatures. Enhanced mixing associated with internal wave packets have been postulated as a mechanism for enhanced nutrient supply and coincident higher biological productivity on continental shelves. Waters of the Australian Northwest Shelf near Ningola Reef are nutrient-poor. The nutrients that are present are rapidly recycled on timescales of hours to days. Physical processes such as upwelling and internal waves have been identified as possible mechanisms for the delivery of nutrients from the deep offshore ocean to the surface nearshore environment. The impact of internal waves on ocean acoustic signal transmission also received attention from oceanographers. The existence of natural variations in the acoustic characteristics of the ocean associated with the presence of internal waves clearly complicates submarine detection. Internal waves can be extremely dangerous to submarines, not only by affecting their signal detections. Accidents caused by internal waves are recorded. For example, in 1963, the nuclear submarine USS Thresher was lost with all hands on board on its takedown cruise. Prior to sinking, there had been no indication of unusual storm weather that could be responsible for this tragedy. Scientists suspect that the submarine probably dropped suddenly to greater depths, as the craft literally slid down the back of the towering internal wave. This happens when the length of the submarine is comparable to the wavelength of the wave. Apart from submarines, constructions in the ocean are threatened as well. Though not as destructive as tsunamis, the larger oceanic internal waves carry a considerable amount of energy, and the associated current flows can be strong enough to be a crucial factor in the design of coastal oil platforms and similar sea structures. Constructions in the ocean, such as drilling platforms, are affected by strong shear currents induced by internal solitary waves, in that the shear currents twist the cables and poles and sometimes damage them. One example is Alexander Keelan platform in the North Sea, which collapsed in 1980, resulting in the death of 123 people. After the accident, people discovered that one of the poles had flopped. In the atmosphere, airplanes experience internal waves too. According to the report by MIT professor Thomas Peacock in 2008, when the Air Canada plane from Victoria to Toronto was cruising in clear skies, neither the pilot's eyes nor the air traffic controller's radar screens saw any severe weather. But, abruptly, the plane plummeted 2,000 feet in 15 seconds, and then another 2,000 before the pilot was able to regain control and level off. The terrified passengers and crew, 10 of whom suffered injuries that would require hospital treatment, had experienced internal waves. Furthermore, internal waves have a significant impact on climate. Turbulent mixing from breaking oceanic internal waves drives a vertical transport of water, heat, and other climatically important tracers in the ocean, thereby playing a vital role in shaping the circulation and distributions of heat and carbon within the climate system. Generally, water is colder, denser at the bottom, while it is warmer and lighter at the top. But internal waves mix the heat and carbon between the layers. Heat and carbon can move between layers due to turbulence in these layers. Microscale turbulence in the upper branch of circulation can redistribute how carbon and heat move throughout the layers. This phenomenon is known as cross-density mixing of water. Thanks for listening to Oceanic Echoes. If you enjoyed listening, please subscribe. Thank you and see you soon.